Great, so let's move on. Next speaker is Emily Denton. Emily is with New York University at the moment, and a few years back she produced the first model that had really impressive Gann samples. But today she'll be speaking about semi-supervised learning with context-conditional generative adversarial networks.
All right. Okay. So, yeah. So yeah, I'm going to be presenting some work I did about half a year ago on representation learning with generative adversarial networks. This is joint work with Sam Gross and Rob Fergus at Facebook AI Research. So I'm going to sort of very briefly kind of skim over the basic adversarial network concept, because I think by this point everybody's aware of it. We have two networks, a generator, a discriminator. The generator produces images, and the discriminator is going to take in a real or a fake image and try and discriminate if it's real or fake. This amounts to this Minimax optimization problem. In practice, as people have mentioned, instead of optimizing this directly, it's common that the generator actually maximizes log D of the generated images. Okay, so the way I view GANs is there's two sort of different perspectives in which you can take. The first, which is I think a lot of the focus of what people have been talking about today, and a lot of the focus of GANs generally, is that you train this discriminator and this generator, and at the end of training, you toss away your discriminator, and what you have is a model that is really good at sampling from some distribution that you've trained it on. And the other view, I think, is where the discriminator is the model of interest. And in this scenario, you can think of the generator as being around to produce sort of optimal negative samples in some sense for the discriminator to learn something about the structure of this distribution that you're training it on. And in this perspective, the main goal is maybe representation learning. So this is going to be the perspective that I'm going to be taking through this talk. So the high-level motivation for this whole work came from the DC Gann paper of Radford et al. In 2016. So they did some sort of preliminary work showing that a Gann discriminator learns a hierarchical image representation throughout the Gann training procedure. So what we did was we asked, okay, how far can we push this? Can we really, learn some kind of useful representation in the discriminator that would maybe transfer to some kind of classification task? So our task is slightly different than the standard generation problem in that instead of determining if a full image is real or fake, the discriminator is tasked with a slightly different problem of determining if part of an image is real given the surrounding context of the image. And one of our motivations for doing this was that at the time it was still really, really hard to generate sort of full images with GANs. And I think it still is in the cases where lots of labeled data is not available. Labels tend to really help shape the images in sort of nice visually pleasing ways. So when we're considering the case where we don't have a lot of labeled data and it is still quite hard to generate large images, and so doing this context conditioning kind of changes the problem in a way that will maybe help us out for classification. Okay, so what we're going to do is we're going to combine this Gann objective with a classification objective and train them jointly. So there's lots of other methods that have added labeled data to Gann training, and some of these have come out after our work and some of them were prior to us. But the basic idea here is there's lots of different ways of doing this. So for example, the original Conditional Gann work, what they did was they just passed a one-hot encoding of the label into the generator. You could also have the discriminator output the number of classes plus one extra for fake data, or you could have your discriminator have two heads, where one has this binary cross entropy, real fake loss, and the other one has this softmax loss over classes. There's lots of different ways you could imagine doing this. The way that we did it, we simply took the discriminator, and after the final convolutional layer of the discriminator, or fully connected, whatever your network architecture is, the network splits off into two heads. One is a classification loss, and then one is this real fake loss, which for us is this binary cross entropy term. So this image here just kind of summarizes standard Gann training versus what we call the semi-supervised Gann training. Something to mention here is that in our model, this classification loss only comes in with real data. So when the generator produces an image and that's passed to the discriminator, that image never goes through this sort of classification pathway. You could imagine alternatives where the classification head is asked to, produce a maximum entropy sort of output for the fake examples, or maybe even try and classify the fake examples as is done in the auxiliary classifier GAN. But we don't focus on any of that. We just sort of have real examples get passed through the discriminator, and we have these two losses. Fake examples get passed through the discriminator, and we just have this real fake loss. Okay, so. Again, most other work that's utilized label data has been using that in a way of improving the image generation, whereas our aim is to improve classification performance. Again, I'll go into this in more detail, but our discriminator and generator are both going to be conditioned on the surrounding context of this image, and the generator is going to be asked to fill in a missing piece. Okay, so just a brief summary of other methods that have learned from spatial context. So a lot of these have come out in the past couple of years. This method was unsupervised representation learning by context prediction, and what they did was they took an image and they broke it up into random patches. They sort of jittered these patches so that neighboring patches didn't directly align and make the problem sort of trivial to solve. And what they did is they had this Siamese network, and the Siamese network takes in two patches from the image and is asked to predict the relative position of patch 1 with respect to patch 2. So this is a classification problem. And then they take this, one of these, the Siamese network, tack a classifier head off that, fine-tune it on labeled examples, and I'll show some examples of how this performs later on. So another method extends this method in some sense, in that it's asking a network to solve jigsaw puzzles. So this is kind of a cute idea, and it actually works very, very well. And what they do is, instead of a Siamese network, they have many, many copies of a neural network, and they break up an image into different patches. They pass all these patches through these networks with shared weights, and then they're asked to rearrange the patches into the correct configuration. And so they frame this again as a classification problem. They have a set number of discrete possible reconfigurations, and so they're predicting which one is the correct one. And then again, at the end of this, you have a neural network, which you can then transfer the features for some other task of interest. So there's another work that was done sort of concurrently with ours, and this is the most related to our work, and this was context encoders. And the idea here is to train an encoder-decoder model, where the encoder takes in the surrounding context of an image and is trained to predict the missing patch. So this is very similar to our work, except that for them, the sort of model of interest that they're going to be using after the fact, the representation that they're going to be learning, comes from this encoder network. So you can think this is sort of analogous to learning, to training an autoencoder with a very kind of structured noising function, and then taking the features of the autoencoder and applying them to some other task. Okay, so again, our task also uses inpainting. We are doing this in adversarial settings. The discriminator is determining if the images are real or fake. And this last point here is just sort of with respect to this context encoding model, we sort of expect our model to maybe work a bit better than theirs, and we see in practice it works a bit better. And our sort of hypothesis here is that this task of determining if an image is real or fake, if the inpainting is sort of a viable inpainting, is a lot more similar to the classification task that we ultimately care about than this sort of inpainting task itself. Okay, so sort of more formally, what our method does is it's basically a conditional Gann. The generator takes in an image, and it's going to have a binary mask. So this symbol here is just a pointwise multiplication. So the generator takes in the image with a mask, with a portion zeroed out. We tried giving the generator also an explicit mask so it would know which part was missing, but that didn't really make any difference. And then the inpainted image is just this xi here. And the discriminator, so this is the standard Gann loss here, binary cross entropy, where we have the real samples as target 1 and the fake samples as target 0. It's exactly the same, except that now the fake examples for the discriminator are now this in-painted image. So one thing to note is that you could think of this as being in contrast to passing in the patch that was produced and the masked out image as separate inputs. We in-paint it and then pass it into the discriminator. So as I mentioned, we make this semi-supervised by just adding this classification objective, and this is just softmax classification. We have a weighting term between these two, so you can kind of trade off and balance between them. So again, this is just sort of comparing what we're doing with, you know, a sort of another alternative semi-supervised GAN. The generator takes in this image, produces the missing patch, and then inpaints the image. And then the discriminator has to determine if that is a real or fake image.
Can you just take us around this diagram a little more slowly?
Yeah.
Because we can't really read the...
Yes. Yeah, okay.
Point to the different things if that's what
Okay, so in a standard GAN, we have this generator, and the generator is taking in a vector that's sampled from some prior noise distribution, typically uniform or Gaussian, something simple and easy to sample from, and the generator is going to turn that into an image. So the discriminator, you can think in the case where it takes in a generated sample, it's going to have a binary cross entropy loss with a target of 1, or sorry, target of 0, because this is a fake sample. And then the discriminator here is taking in a real sample from the data set. And the only difference from a standard GAN is that we also have this classification objective on the top here. And so the idea is that when real samples are going into the discriminator, we optimize for the classification loss and also the discrimination of real and fake. And for the generated samples, we only optimize this real and fake. And in this setting here that I just described, only the discriminator is being updated. Then when we want to update the generator, it's optimized so that it fools the discriminator. And then the difference here with the semi-supervised GAN is that now the generator is taking in two things. It's taking in, again, this noise vector, analogous to before, but also this image here where a randomly chosen hole has been masked out. So in this case, it's just a single hole that's removing a quarter of the image, but you could imagine taking out different sized patches from different places. There's a bunch of different schemes you could use here. And then the generator is going to output a full-sized image, the same dimensionality as the input, but only the part that was masked out is going to be used to fill in the image. And so that's why, for example, this is actually something that the network produces. You can see that all of these things, all of these pixels outside of the masked out hole are kind of garbage because it has no incentive to sort of fill them in with anything reasonable. But as you get closer to this hole here, then you see it produces something that makes sense. And then, again, the classification objective comes with the real images. So, okay, so now this is just a really quick comparison to the context encoder model because that is the most similar to our approach. And the things to highlight here is that, so the blue encoder here and the blue discriminator here play analogous roles in the sense that they are learning the feature representation that we care about. So here we see that there's this encoder and the classification loss is tacked onto that, whereas for us we have this discriminator and the classification loss is tacked onto that. Okay, so I'm going to try and rush through these. So then we have one sort of extension of this, which empirically works a bit better. So in this model here, I was showing the discriminator. It takes in this in-painted image. So in this case, a large portion of the image is a real image, and then some patch of it has been produced by the generator. But you could imagine also passing in this full image here that was produced by the generator as well into the discriminator. So that's what we do, and this works a little bit better. So we called this CCGainSquared because it's kind of combining the GAN and the CCGain, and we had no better naming schemes. So the idea here is that now these first two lines correspond to what I was showing you before, where the real samples come from the data set and the fake samples are these in-painted images, but now we're also giving the discriminator in-paint the entire generated image. And so you could have a trade-off term here. In practice, we just set alpha to be 1/2. So half of the fake examples that the discriminator gets are in-painted, and half of the fake examples that the discriminator gets are this full image. But in both cases, the generator is still getting the context. And so the generator has a lot more information than it does in the original GAN formulation. And so I'll show at the very end sort of examples of what it looks like, the actual images that are generated when you use these schemes. Okay, so one final thing, GAN still kind of struggle to generate large resolution images, and so one thing we did for one of our bigger data sets was also condition on a low resolution version of the full image. And so the key thing here is that the discriminator doesn't get this as input, so the problem for the discriminator does not change here. We're giving the generator a little bit of extra information, but the discriminator is still faced with the exact same problem. And this is pretty important because this is kind of like what we care about. We don't care about being able to generate these, in-painted images. What we care about is learning a discriminator that's going to be, learn useful representations. Okay, so this is just our architecture. It is kind of hard to see, but basically it's a VGG network. It's the smallest VGG network with the fully connected layers removed. And then our generator was like a DC Gann style generator. Okay. So we tested this out on 2 data sets. The first was STL10. This is a pretty commonly used data set for semi-supervised learning or unsupervised learning because it comes with, the data set is quite small, so there's 10 different folds of the data, each of which has 1,000 labeled examples, but then there's 100,000 unlabeled examples, which come from a broader distribution of classes than the labeled examples. So this is really nice that we can leverage all of this unlabeled data. And then the second data set that we used is Pascal. So there's 5,000 training and validation images here. There's a lot of variability in sort of object size and pose and lighting conditions, and there's multiple labels for each image. Okay, so first I'm going to go through some results on STL10. So the basic training setup here is that you train 10 models on each of the predefined folds, and then report the mean and standard deviation of the test accuracy. So that's where these means and error bars are going to come from. So what we did was we trained models on 64 by 64 crops of the 96 by 96 images, and the whole size was 32 by 32 pixels, and this was randomly chosen, like a random location in the image. I also ran a bunch of experiments where I tried taking smaller patches as holes, but multiple holes kind of works comparably. As long as the hole size is sort of big enough that the problem is, challenging, things kind of worked. And then we fine-tuned the classifier on the full resolution 96 by 96 images. Okay, so these are our results. So the supervised VGG network that we trained got 61%, and then this SSL-Gann here refers to just a regular Gann, but with this semi-supervised loss. So this is sort of, I think in some sense, an important number, because this is showing that the Gann objective alone really gets you quite a ways. It doesn't quite beat these other methods that have been proposed. I'll mention, so the wetware autoencoder, this is like an autoencoding scheme, except a little bit more sophisticated because the encoder gets to pass sort of location information to the decoder. And this exemplar CNN, this was work from a couple years ago. It was quite interesting, actually. The idea was to take your training set and for each image, perform a whole bunch of different data augmentation techniques. So different crops, different image contrast techniques, and then pass all of those augmented images as one label to the classifier. So if you had, 5,000 images in your training set, then you'd have 5,000 different classes, and each of the instances for each class would be a different sort of augmented version of the image. So that works quite well. Anyway, so the Gann gets almost as good as that, but not quite. And then when we added this context conditioning, we did a lot better. And then when we combined this context conditioning with the sort of regular Gann with our CCGainSquare, we get a pretty big improvement over other approaches. So this is an example of some of the in-painting results. Again, this is sort of hard to see, but the idea here is just that we're producing sort of semantically meaningful in-paintings. Even though in-painting isn't our goal, it's sort of used as this proxy task, and we end up with fairly nice in-paintings. So the top row here shows the masked out image, and the bottom row here shows the in-painted image. And then at the bottom here, we can see this top row is the masked out image, this second row is the in-painted image, and in this bottom row here is the actual output of the generator. So in this case, the output of the generator itself is sort of consistent with this conditioning image, but the entire image itself kind of looks like a generated image. Yeah.
Yeah, super quick question. So in the Gann, do you use the 100,000 images extra that you have?
Yes, yeah.
Why do you not use that?
We haven't tried that, actually. Yeah, we haven't tried that. But I'll say something sort of about that when we come to the Pascal, because with Pascal, a lot of the methods we're going to compare against, they do use extra data, and with Pascal, we only use the Pascal training set. But in this case, yeah, we use the 100,000 to do this context conditioning. Okay, I'm going to rush through. Okay, so for Pascal, this is the sort of standard way of evaluating Pascal. I'm just going to say that. And so our best models we trained on 128 by 128 resolution images from Pascal, and we used 64 by 64 whole size and a 32 by 32 low resolution image. So this kind of just compares all of our models using these different, variants. And you can see this low resolution conditioning helped a little bit when we got up to really high res images. It didn't help a lot. You can see like 61.3 to 62.2, but we still put this in there because maybe, this is useful for, future work. And okay, so now comparing to some other methods. So this is comparing against the other sort of context conditioning methods I presented at the beginning. And you can see, so the reason I put this supervised AlexNet is that most of these methods used AlexNet as their architecture, whereas we used VGG. So we have this sort of supervised AlexNet and the supervised VGG numbers as a way of sort of trying to compare these different methods in a somewhat fair manner. But you can see that we get quite a big improvement over just supervised VGG. And this sort of CCGainSquare improves a little bit over just the plain CCGain, but not that much. And then, so I'm going to go to another slide that's going to have these plus more results because there's actually been a lot of improvement on the Pascal data set, and a lot of it's due to this new sort of initialization approach. A lot of these old methods have been rerun with this sort of data-dependent initialization method, and really, really improved things. So this is sort of the better way of putting our work in context of all of these other methods on Pascal. So this is showing the original numbers that I was showing from the previous slide and as they were reported in this paper here. And then these are showing improvements with this new initialization method. So the best now is this jigsaw solving puzzle, which they didn't have any results when we wrote this paper, but they have a new version where they use this initialization method and they do really well and outperform everybody else. And then these other methods that were below us now with this initialization method are closer to our results. So another thing I should mention about this is that, so all of these other methods, they use external data during their training. So I believe this sort of context prediction and context encoders and jigsaw solving, I think they all use ImageNet. And then this visual tracking from video, they use a bunch of video data. And we don't use any extra data. We haven't tried our method using extra data. Okay, almost done. We haven't tried our method with extra data, but that would be sort of interesting to see. But it's kind of cool that we get these improvements just using Pascal. And then another thing to mention is the training time of all of these. So I believe the context prediction takes a very long time to train, many weeks. The context encoders is much more comparable to ours. I think it's maybe double the time, but it's still on the order of like 6 to 8 hours for ours, and I think they report 14 hours. And the jigsaw puzzle solving one, this is the one that had all of these replicated networks that takes in all the patches of the image and unscrambles them. That takes 2.5 days, which is still a lot longer than ours, but actually not too unreasonable, and they see a really big improvement. So those are all of our results on Pascal. And then just to give you a sense of the inpainting, again, the point of this is just to show that the inpaintings are pretty semantically meaningful. So you can see this is sort of like a horse, and it's kind of filled in as a horse. And again, we're not trying to show that this is what you should use for inpainting. You should probably use some kind of combination of perceptual loss metrics and mean squared error and all these things if your goal is inpainting. But this shows that our generator is sort of learning nice semantically meaningful inpaintings. Okay, so just a couple of final comments. Again, the basic idea of this was that this is a super, super simple semi-supervised learning framework. The cost of training is not that much more than just training a regular classifier. You have this sort of generator network as well, but that's it. It's fairly simple. Of course, there's the caveat of you're adding in this adversarial loss, so things can get weird and unstable. But doing this context conditioning tended to make things more stable overall. So this is a very simple method. And then sort of more generally, I think that there's an interesting question here of like, why is this adversarial discrimination a useful task for classification? Sort of intuitively, it kind of makes sense that solving this discrimination task requires learning something about the structure of natural images, and doing this context conditioning sort of frames the problem as, what object parts should be there if you see this other object part. But I think that generally representation learning with GANs is super underexplored, and I think it's really interesting that, in order to learn these generative models, we're learning these really, really powerful sort of discriminative functions, and then we're just throwing them out at the end of the day and not using them for anything. So yeah, if you take away anything, I think it's, this is a really interesting area of research that, we should explore further. And then finally, there's been a ton of work that a lot of people have mentioned on tricks for improving GANs. A lot of these could be combined with our method. A lot of them might be a little bit tricky, like a big component of the WGAN is this Lipschitz constraint, so maybe that would, inhibit the classification performance. But there's a bunch of these methods, and some of them are orthogonal to ours, and I think the sort of representation learning with all of these different things is really interesting. And then one final thing, we aren't the only people to have really looked at this representation learning problem with GANs. We're the only ones to really kind of push it from the perspective of looking at the discriminator features. But there's these two papers, adversarially learned inference and adversarial feature learning, and they try to do representation learning with GANs, but using the generator. So they learn an encoding network and use the feature space that the generator is learning for representation learning. So yeah, there you go.
We do have time for one or two questions.
Yeah, just an understanding question. So
Yeah.
in the CCGainSquare, does the discriminator get information on the mask location or no?
Not explicitly. So not explicitly. Because we inpaint the image and then give the fully inpainted image, it doesn't explicitly know where the boundaries are. We did this because we thought that if we were to give the two pieces separately, then it would be really, really simple for the discriminator to just identify where the discontinuities are along the kind of mask edges. So that's why we did it. Yeah.
So related question, does the size of the inpainted region matter? And how do you handle that?
Yeah, so the answer is it does to a certain extent. So in all of my preliminary experiments, I played around with removing a patch size that was basically a quarter of the image, and other variants such as removing smaller patches, but between like 1 and 5 bits of smaller patches. We always removed squares. You could do something more sophisticated like remove full objects, but we didn't. But basically all of the things that I saw was that if you removed too little or too much, then it didn't perform very well. And then when you were kind of in this sweet spot in the middle, it didn't really matter if you removed a bunch of small patches or one big patch. But as long as you removed, roughly like a quarter of the pixels overall, depending on, the different scheme, it kind of worked.
All right, then let's thank Emily again.